What you are seeing is not movie special effects. This is reality unfolding at a height of 359 meters above the Chenab River level. Located deep within the Himalayan mountains, this project is a testament to human ingenuity and engineering prowess.
To understand the scale, if we place the Eiffel Tower here, its top would still be 35 meters below the bridge deck.
This is the Chenab Bridge, the highest railway bridge on the planet, standing as a marvel of modern construction.
But the height and the $5 billion budget are not even the craziest parts of this incredible engineering project.
What truly makes engineers hold their breath is its location in the Jammu and Kashmir region, a harsh environment.
This is one of the most challenging places on Earth to build, isolated from the civilized world.
Engineers had to contend with high-magnitude earthquakes, destructive wind speeds, and complete isolation during the entire construction phase.
How could humans transport 30,000 tons of steel through vertical cliffs with no roads?
Why did engineers choose a steel arch structure instead of the usual cable-stayed or suspension bridge?
And how do you hang massive steel blocks weighing tens of tons in mid-air with millimeter precision?
In this video, we will explore together how Indian engineers built the highest bridge on the planet. Before we start, don't forget to like and share this video with more people.
Now, let's get started right away.
To start this project, the engineers had to solve the first problem: access. The construction area was so remote that previously no roads existed. Therefore, the mandatory strategic move was building a 26-kilometer service road cutting through the Rocky Mountains. First, worker teams had to use specialized ropes, hanging themselves directly on the vertical cliffs. They used handheld drills to create holes for explosives deep into the mountainside. Then, controlled blasting techniques were activated to peel off hard granite layers precisely.
As soon as the dust settled, small crawler excavators immediately entered the danger zone.
Here, the operator had to both push tons of rock into the abyss and be cautious every inch.
Specifically, as they progressed, they had to install steel mesh and spray concrete to reinforce the cliff face. Just like that, every meter of road was wrestled from nature's grip.
After the road was completed, let's talk about materials.
The total amount of steel needed for this project amounts to 30,000 tons. However, bringing this massive amount of steel from the factory to the mountain peak was a terrible challenge. Look at the hairpin turns on the single road we just opened. The turning radius is extremely narrow.
Therefore, the engineers were forced to choose the solution: on-site fabrication.
Steel was cut into compact module plates right at the factory to fit the truck bed size. Upon arrival, a massive field workshop was erected right on the edge of the cliff. Here, welders would start joining each small piece back into complete structural components for assembly.
When tens of thousands of tons of materials were fully gathered, the vital technical question truly began.
What type of bridge will we build? The engineers had to face the biggest enemy in this valley: wind.
Survey data showed that wind gusts here could reach 266 kilometers per hour, equivalent to a major hurricane.
Initially, many suggested cable-stayed or suspension bridge options because they are common and easier to construct. However, in bridge engineering, these two types have a fatal flaw. Their structure is very soft and flexible.
Therefore, After many calculations, the optimal and only solution selected was the steel arch structure.
Unlike suspension bridges, which withstand tension, arch bridges operate on the principle of compression.
The bow shape gives it extreme structural stiffness. It remains rigid and solid, not deforming under wind pressure.
The entire weight of the train and the bridge will be converted into compressive force, transmitted along the two arch ribs.
To realize this design, the first construction stage undertaken was foundation work.
Engineers had to dig deep into the rock face, pouring thousands of tons of reinforced concrete to create two eternal pedestals. They anchored the bridge feet tightly into the mountainside, turning the Himalayan cliffs into part of the load-bearing system.
The foundation was done. Now it was time to assemble the backbone of the structure, the massive steel arch.
But with the distance between the two cliffs reaching nearly 500 meters, no crane could reach.
To solve this, engineers had to create a giant tool themselves, a cable crane system spanning across the sky. First, they erected two towering steel pylons on the opposite peaks.
Engineers had to deploy a specialized helicopter, flying from one bank to the other to drop a pilot wire.
This tiny pilot wire acted as a guide. It was connected to a powerful hydraulic winch system to pull a larger cable. When the cable system was tensioned, the sky above the site officially turned into a mobile assembly plant.
Now the trolleys on the cables started working. They picked up each steel arch segment from the yard.
The erection process was carried out simultaneously from both banks, reaching out to the middle of the river.
To keep these heavy steel segments suspended in the sky, engineers used a temporary stay cable system.
After the hollow steel tubes were positioned, high-pressure fresh concrete was pumped to fill the inside.
This combination created a super strong structure. The steel shell withstands tension. The concrete core withstands compression.
The most dramatic moment of the project arrived when the two arch halves met in the middle of the valley.
When the final locking pin was closed, the arch officially became a unified block, standing firm.
Now it was time to construct the deck, where trains would directly roll.
Engineers used the incremental launching method. The process went like a continuous production line.
A massive hydraulic jack system would push the segment to slide out towards the abyss.
When the final locking pin was closed, the arch officially became a unified block, standing firm.
The final piece for this structure to survive for 120 years is solving the problem: temperature.
In this mountain region, the temperature changes drastically from 0 degrees Celsius to 50 degrees Celsius.
To neutralize this, engineers installed a spherical bearing system at the contact points between the deck and pillars.
This device works exactly like cartilage joints in the human body, allowing the deck to slide freely.
So, we have walked through the entire journey of building a masterpiece.
From the first rock-blasting drills to the precise launching technique, the Chenab Bridge is a proof of human intellect.
In this entire risky construction process, which stage impressed you the most?
Leave your analysis in the comment section below. Don't forget to like the video and subscribe to the channel to fuel us for the next mega projects.
In this mountain region, the temperature changes drastically from 0 degrees Celsius to 50 degrees Celsius.
you.